Good day and welcome to our presentation. My name is Stella Graßhof. I'm presenting our joint work from Sami S Brandt and myself. We are both from the Department of Computer Science at the University of Copenhagen. And it's my great pleasure to present you our work with the title Tensor-Based Non-Rigid Structure for Motion. So first off, we will start off with a data array. So here we will actually sort 2D data points into a 5D dimensional array, which we will refer to as data tensor. And in fact, you can unfold the data tensor into different matrices. And each of these unfoldings can then be factorized using an SVD. And if we do this for each of the unfoldings, then this is called the higher order singular value decomposition. And when we do this for each of these data dimensions, we can actually gain insights with respect to the different subspaces. Here specifically, the first is the data dimension, which would be 2, because we're actually looking at 2D data points. Then the number of points, which would be 7K approximately for this specific example, which you can see on the slide, because we have around 7,000 2D points. Then the number of samples, which is the number of repetitions of recordings. Then the number of persons and their expressions, which they're actually performing. And here again, a reminder that this can be done with different kinds of data, yet we're focusing on faces. When we now unfold this data tensor in different ways, we found that actually one of these unfoldings is a representation of the data matrix, which is usually factorized in traditional non-rigid structure from motion approaches. In fact, here you are looking at phase shapes, but in actuality, we're actually factorizing the matrix with phase shapes which have been centered at the rigid shape. So you can consider this kind of a mean-free data. And we factorize this, as traditional methods also do, in some kind of projective information and 3D representation. And on the left, you can see MI are the affine projections, which are actually 2 times 3 matrices. And alpha IK are scalar coefficients, which represent the weight coefficients. And on the right-hand side, you can see the 3D rank 1 basis shapes. And also here, these here are actually centered at the rigid shape. And here, these are actually the main contribution of the paper, because we represent these ring 1 basis shapes as a product of 2 vectors. Hence, this is actually rank 1. And this is in contrast to other works where they actually use a reordered 3 times n matrix. And then this is actually rank 3 in contrast to what we are doing here. So again, to focus on this specific part, we have the basis shapes, which are the sum of a rigid shape and a product of a 3 vector, which actually performs a back projection of a shape component, BK, and this shape component is actually a perturbation from the rigid shape, which can be computed as a singular vector from the measurement matrix by using SVD on that. So that's the shape component, which is actually the perturbation from the shape. And if we now compute this product between this 3 vector and the shape component, we'll get the perturbation with respect to the rigid shape. And this can then be applied. So we actually apply the matrix-based and the tensor-based approach to here reconstruct dense 3D shapes from sparse 2D landmarks. And we can not only do that, but in fact, we can take advantage of the strength of the matrix-based approach and the tensor-based approach, and then also change the expression and thereby generate unseen new shapes and synthesize also persons and expressions which are not in the database. And with this, I want to thank you and conclude my talk. We are looking forward to see you at our poster.